Welcome back to the deep dive. It is great to have you with us. Today we are wrestling with a ghost. We're talking about something that is effectively everything, and yet for us here on Earth, it's frustratingly close to being nothing. We are unpacking the ultimate paradox of the periodic table.
That is the perfect way to frame it.
Yeah.
Yeah. It's the element of contradictions.
Yeah.
We are looking at an element that makes up what? Roughly 75% of all normal matter in the universe.
75%.
It's the fuel of the stars, the simplest chemical structure possible. And yet, here on Earth, it's elusive, it's difficult to catch, it's a nightmare to store, and for the last century, we've mostly had to manufacture it ourselves using pretty dirty methods.
Exactly. It's the most abundant thing out there, but if I want a tank of it, I have to go through this massive industrial process to get it. We are talking, of course, about hydrogen. Symbol H, atomic number 1, the OG element.
The OG element is a very fitting description. It really is the starting point of chemistry.
And the mission for this deep dive is, well, it's pretty massive. We want to unpack how this single proton-electron duo, which formed shortly after the Big Bang, is currently trying to revolutionize our energy grid. It's literally feeding the entire human population, and it's giving engineers massive headaches because of its weird quantum behaviors.
It's a journey from the birth of the cosmos to the inside of a fuel cell in a modern bus. And along the way, we have to deal with invisible fires and metals that turn to dust.
I have to say, one of the things that stuck out to me in the research, and I just can't get this out of my head, is the idea that water, the stuff we drink every day, is basically just hydrogen ash.
That's
What's left over after hydrogen burns.
That is a very dramatic but chemically accurate way to put it. When hydrogen burns, it reacts with oxygen. The energy releases the fire, and the exhaust, the residue, is H2O.
So water is just exhaust.
Water is the exhaust of hydrogen combustion. But I prefer to frame it as the fundamental building block. If you understand hydrogen, you really start to understand the architecture of the universe itself.
Okay, let's unpack this. Before we get to the rocket ships and the green energy revolution, we have to go back, way back. Not just to the Big Bang, but to the humans who first realized this gas was actually a thing. Because for a long time, we didn't even know it existed. Right?
We didn't. Yeah. Which is strange considering how reactive it is. If you look at the history and etymology, the name itself tells a story. Hydrogen comes from the ancient Greek. Hudur, meaning water, and genaj, meaning I bring forth or I create.
So literally water former.
Exactly, water former. But that name didn't come until much later. The discovery timeline is really a comedy of errors. You have to go back to 1671. Robert Boyle, the famous chemist, is in his lab.
Okay.
He drops some iron filings into dilute acids.
A classic chemistry set experiment. You see bubbles.
Right. And he sees bubbles. He sees this gas coming off. But he doesn't realize he's discovered a new element. He just describes the reaction. He misses the significance that this gas is flammable. He essentially sees the smoke but misses the fire.
So he sees it and notes it down and just moves on. When do we actually realize, hey, this is a distinct substance?
That takes nearly another 100 years. 1766. Henry Cavendish. Now, Cavendish is a fascinating character in the history of science. He was incredibly wealthy, painfully shy likely on the autism spectrum by modern standards, and an absolute genius. He isolates this gas, and he calls it inflammable air.
Inflammable air. Catchy.
And here's where it gets really interesting and, slightly ironic. Cavendish was a believer in the phlogiston theory.
Oh, phlogiston. That was the hypothetical substance that people thought existed inside things to make them burn, right? Like wood had phlogiston in it and burning just released it.
Precisely. It was a completely wrong theory, but it was the scientific consensus of the time. Cavendish speculated that this inflammable air he found was actually pure phlogiston. He thought he had isolated the essence of fire itself.
So he discovers the most fundamental element in the universe, and his conclusion is, I found the magic fire ghost particle.
Essentially, yes. But he did notice something crucial. When he burned this inflammable air, it produced dew.
Water.
Water.
Which shouldn't happen if it was just fire stuff. Fire shouldn't turn into water.
Exactly. And that is where Antoine Lavoisier comes in. In 1783, he reproduces Cavendish's experiment. He realizes that this gas isn't phlogiston. It is a unique element that, when combined with oxygen, creates water. So he gives it the name hydrogen,
Water former.
water former.
And once we knew what it was, we started using it pretty quickly.
We did. That same year, 1783, we see the first hydrogen balloons.
Right.
By 1806, we have the first internal combustion engine running on hydrogen-oxygen mixture.
Wait, 1806? We had hydrogen engines before we had gasoline engines.
We did. The Derivaze engine. It wasn't very practical, but the concept was there. Hydrogen has been an energy carrier for a very, very long time.
But obviously the early usage hits a major snag. We can't talk about hydrogen history without talking about the big floating elephant in the room.
The airships.
The airships.
The Zeppelins. Hydrogen is the lightest element, so it provides incredible lift. It's only about 7% the density of air. For decades, it was the standard for lighter-than-air travel. But as we know, hydrogen is highly flammable.
And that leads us, of course, to the Hindenburg disaster in 1937.
Which effectively ended the era of the hydrogen airship. It caused a massive shift toward helium, which is non-flammable but much rarer and more expensive. It's a classic case of safety overriding utility. We chose the heavier, more expensive gas because we didn't want to explode.
So we have this element that we identified, named, used to float around, and then realized was incredibly explosive. But let's zoom out, like way out. You mentioned earlier that this is 75% of the universe.
That's right. If you count by mass, it's 75%. If you count by the sheer number of atoms, it's more like 90%.
That is mind-boggling. Where did it all come from?
It is the primordial element. In the chronology of the universe, protons formed within the first second after the Big Bang. But neutral hydrogen atoms, where an electron is actually bound to a proton, they formed about 370,000 years later.
370,000 years seems like a long time to wait for the first atom.
In cosmic terms, it's a blink of an eye. This period is called the recombination epoch. The universe expanded and cooled just enough for that plasma to settle down into atoms. And from those clouds of hydrogen, gravity started to pull them together to form stars.
So stars are basically just massive hydrogen-burning furnaces.
Fusion furnaces, yes. They fuse hydrogen into helium, releasing massive amounts of energy. That's sunlight hitting your face right now. That is the result of hydrogen fusion 93 million miles away.
Okay, so it's in the stars, it's in the interstellar medium, but what about closer to home? What about in our own solar system? I saw something in the notes about Jupiter that sounded like, well, science fiction.
Ah, yes, metallic hydrogen.
Metallic hydrogen. That sounds like a heavy metal band, but what is it actually?
It is a state of matter that we can barely comprehend on Earth. Deep inside giant planets like Jupiter, the pressure is unimaginable. We're talking about 400 million pascals of pressure.
And what does that do to the gas?
It squeezes the hydrogen atoms so tightly together that they behave like a metal. The electrons become delocalized, meaning they can flow freely through the structure. So inside Jupiter, hydrogen conducts electricity. It creates this massive magnetic field.
So if I could survive the pressure, which I obviously couldn't, I would be looking at a sea of liquid metal hydrogen.
Essentially, it's a mind-bending concept.
Yeah.
But on Earth, the story is very different.
Right, because if I go outside and take a deep breath, I'm not inhaling much hydrogen, am I?
Very, very little. It's present in the atmosphere at about 0.5 parts per million.
That's basically nothing. So why is it so rare here if it's so common everywhere else?
Gravity. Hydrogen is just too light. Earth's gravity isn't strong enough to hold on to it in its gaseous form, H2. Over billions of years, most of the free hydrogen gas simply floated up to the top of the atmosphere and escaped into space.
It just drifted away.
It did. So on Earth, hydrogen is almost exclusively found in compounds. It's locked up in water, H2O, and it's locked up in hydrocarbons, fossil fuels. To get hydrogen here, we have to break those bonds. We have to liberate it.
Okay, so we've established it's the Houdini of elements. It escapes Earth. It changes states inside Jupiter. But when we do capture it, it gets even weirder. I want to talk about this quantum weirdness section because this blew my mind. Hydrogen isn't just hydrogen.
No, it is not. This is a detail that often gets overlooked in basic chemistry, but it is absolutely critical for anyone trying to work with liquid hydrogen. We're talking about spin isomers.
Spin isomers. Okay, lay it on us.
So, hydrogen molecule, H2, has 2 protons in the nuclei. Protons have a quantum property called spin. You can think of them like little spinning tops.
Okay, I'm picturing 2 spinning tops.
Yeah, there are 2 ways these spins can align. If the 2 protons are spinning in the same direction, parallel. We call that orthohydrogen.
Ortho, same direction, got it.
If they're spinning in opposite directions, anti-parallel. We call that parahydrogen.
Para, opposite. Okay, why does this matter? Who cares which way the protons are spinning?
The universe cares because they have different energy levels. Orthohydrogen has more energy. At room temperature, hydrogen gas is about 75% ortho and 25% para.
Okay, so normal gas is mostly ortho.
Right. But here is the catch. The why this matters moment.
Hmm.
Orthohydrogen is unstable at low temperatures. If you cool hydrogen down to turn it into a liquid, which you have to do at minus 253 degrees Celsius,
Which is incredibly cold.
incredibly cold. When you do that, the orthohydrogen naturally wants to convert into perhydrogen.
Okay, so it changes its spin. What's the big deal?
The conversion releases heat. It is exothermic.
Wait, so you cool it down to make it a liquid,
Yeah.
and then it spontaneously releases heat.
Precisely. And the amount of heat released by that conversion is actually greater than the heat of vaporization of liquid hydrogen.
So if I just cool it down and put it in a tank?
The conversion heat will boil the liquid hydrogen away.
No.
You spend all this energy liquefying it, and then it boils itself off from the inside out because of quantum spin flipping.
That is incredibly frustrating. It's like the element is actively fighting you.
It is. That is why, in industrial liquefaction, they have to use special catalysts like ferric oxide during the cooling process. These catalysts force the conversion from ortho to para while it is being cooled, so the heat can be removed by the refrigerator. If you don't do that, you lose your fuel.
That is a wild level of complexity for the simplest element. It's not just make it cold. It's make it cold and flip the spins.
It highlights just how unique hydrogen is. No other element gives us this specific headache.
So speaking of headaches, let's talk about how we actually get this stuff. We established it escapes Earth, so we have to make it. And right now we are mostly making it from the very thing we are trying to replace, right?
Unfortunately, yes. This is the reality of the colors of hydrogen you might hear about. Right now, the vast majority of hydrogen production is what we call gray hydrogen.
Gray hydrogen, which comes from fossil fuels.
Specifically, natural gas. We use a process called steam methane reforming, or SMR. We take methane, CH4, and blast it with high-temperature steam.
And that just rips the hydrogen off the carbon.
Exactly. You get hydrogen gas, but you also get carbon monoxide and, eventually, carbon dioxide.
How much CO2 are we talking about here?
It is significant. For every 1 ton of hydrogen you produce this way, you are generating between 6.6 and 9.3 tons of CO2.
Wow, so nearly 10 times the weight in pollution? That kind of defeats the purpose if you're trying to be green.
Which is why there is such a push for green hydrogen. This is the cleaner alternative, electrolysis.
This is the high school science experiment again. Stick 2 pencils in water, hook up a 9-volt battery.
On a much, much grander scale, yes. Use electricity to split water, H2O, into hydrogen and oxygen. If that electricity comes from renewable sources, wind, solar, then the hydrogen is effectively carbon-free.
So why aren't we doing this everywhere? What's the holdup?
Cost. It is much more expensive than steam reforming. And it requires expensive catalysts, usually platinum or iridium, though nickel is being used more. It is an economic battle right now.
But there are some weirder ways to make it, right? I saw biohydrogen in the notes. Are we talking about like hydrogen farms?
In a way, certain bacteria and algae naturally produce hydrogen. They have enzymes called hydrogenases.
Hydrogenases?
These enzymes allow them to essentially exhale hydrogen under certain conditions. There are even bacteria like Mycobacterium smegmatis that can survive by consuming the trace amounts of hydrogen in the air.
Wow.
So we are researching ways to harness these biological processes to produce hydrogen for us.
That's incredible. A bacteria breath powering a car. But there's another source that I think is the most provocative. We always assume we have to make hydrogen, but the outline mentions a geological surprise.
This is a very recent and exciting shift in geology. For a long time, the dogma was that pure hydrogen gas doesn't exist in the ground. We thought it was too reactive, that microbes would eat it or it would react with rocks.
But we were wrong.
We were. We are discovering natural geological processes, specifically something called serpentinization.
Serpentinization, great word. What is happening there?
It happens when water meets iron-rich rocks deep underground. The water oxidizes the iron, essentially rusting it, and in that chemical reaction, hydrogen gas is released.
So the Earth is naturally producing hydrogen factories underground.
Correct. And we have found large deposits. There is a famous one in Mali. There are findings in France and Australia. People are starting to use the term gold hydrogen or white hydrogen.
Like the gold rush?
Exactly. If we can tap into these natural reservoirs, it could completely change the equation. We wouldn't have to make it from dirty gas or expensive electricity. We could just drill for it, like we do for oil.
That sounds almost too good to be true.
Well, the economic extraction is still uncertain. We don't know how fast it replenishes or how easy it is to capture. But it challenges the assumption that hydrogen is just an energy carrier. It might be a primary energy source.
That is a massive distinction. Okay, so let's assume we have the hydrogen, whether we made it, grew it with bacteria, or drilled it out of a rock in Mali. What are we actually doing with it? Because I think most people hear hydrogen and they think cars.
Cars are the visible tip of the iceberg, but they are actually a tiny fraction of current use. If you want to know what hydrogen is really doing, look at your dinner plate.
My dinner plate.
Approximately 50% of the nitrogen in your body came from the Haber process.
The Haber process, this is for ammonia production.
Yes, the single biggest consumer of hydrogen today is the production of ammonia, NH3, for fertilizer. Without synthetic fertilizer, we simply could not support the global population.
So hydrogen is literally feeding the world.
It is the bridge between the nitrogen in the air
Yeah.
and the food on our table. It is absolutely essential for modern agriculture.
That's high stakes. What else?
Well, the most glamorous use is rocket science.
Of course.
Liquid hydrogen is the fuel of choice for high-performance rockets. The space shuttle main engines, for example. When you mix liquid hydrogen and liquid oxygen, you get the highest specific impulse, the most bang for your buck in terms of thrust efficiency of any chemical rocket fuel.
And the exhaust is just steam.
Superheated steam, yes. Which brings us to the energy carrier role, fuel cells.
This is the dream of the hydrogen economy.
A fuel cell creates electricity by combining hydrogen and oxygen, but instead of burning them in an explosion, it controls the reaction chemically. Electrons are stripped off the hydrogen, forced through a circuit to do work, like turning a motor, and then reunited with oxygen on the other side.
And again, the only emission is water vapor.
It is incredibly clean at the point of use. We're seeing this scale up in buses, trains, and potentially heavy shipping in aviation areas where batteries are just too heavy.
Right, because batteries are heavy. Hydrogen is light. If you need to fly a plane or push a cargo ship across the ocean, hydrogen or synthetic fuels made from it might be the only way to decarbonize.
There are also some really fascinating niche uses. For example, did you know hydrogen is used as a coolant in electrical generators?
A coolant? But it's flammable.
It is, which sounds counterintuitive.
Yeah.
But hydrogen has the highest thermal conductivity of any gas. It is incredibly good at moving heat away. And because it has such low density, it creates very little wind resistance or windage loss on the spinning rotors of the generator.
So giant power plants are cooling their generators with explosive gas because it's slippery and conducts heat well.
Precisely. They just have to be very careful to keep the air out so it doesn't ignite.
And I saw one other niche use that surprised me, the food industry. E949.
Yes. Hydrogen is an authorized food additive. It's used as a packaging gas.
A packaging gas.
It prevents oxidation. If you have fats or oils in the food, oxygen will make them go rancid. Hydrogen helps protect them. It's also used in the hydrogenation of fats, like making margarine, though that is a chemical reaction rather than just packaging.
It's everywhere. In the rockets, in the generator, in the fertilizer, in the margarine. But we have to talk about the dangers. We touched on the Hindenburg, but the safety reality check in the source material is fascinating. Specifically, the invisible danger.
This is something that terrifies people who work with pure hydrogen.
Yeah.
Hydrogen flames emit very little radiant heat, and, crucially, they emit light almost entirely in the ultraviolet range.
So, in daylight,
You cannot see the fire.
that is the stuff of nightmares. How do you even know it's there?
There are stories from the early days of hydrogen research where workers would walk around with a broom held out in front of them.
A broom.
If the bristles started burning, they knew there was a hydrogen leak and a fire right there.
The broomstick method of fire detection.
Low tech, but effective. Nowadays, NASA and industry use specialized flame detectors that can see the UV and IR signatures. But imagine walking into a flame you can't see.
And it's not just the fire, it's what hydrogen does to the pipes holding it. Embrittlement.
This is a materials science nightmare. Hydrogen atoms are so small that they can diffuse into the crystal lattice of solid metals like steel.
They just wiggle their way in between the iron atoms.
They do. And once they are inside, they create internal pressure. They can form little pockets of gas inside the metal, causing it to crack and shatter essentially from the inside out.
So you can't just put hydrogen in a regular natural gas pipeline.
Not easily. You need special coatings or specific alloys that are resistant to hydrogen attack. It makes the infrastructure challenge much harder than just switching the tap from gas to hydrogen.
And then finally, the explosivity. We know it burns, but the range is wide, isn't it?
Extremely wide. Gasoline fumes need a very specific ratio of air to burn. Hydrogen will burn in air at concentrations anywhere from 4% to 74%.
So almost any mixture is a bad mixture.
However, there is a saving grace. Remember how light it is?
It floats up.
Exactly. If you have a gasoline leak, the fumes pool on the ground, waiting for a spark. If you have a hydrogen leak outside, it rises and disperses into the atmosphere at 20 meters per second. It flies away from the danger zone very quickly.
So in a way, it's safer in an open crash than gasoline might be.
In an open environment, yes. In an enclosed space,
Yeah.
oh, that's a different story.
Okay, so let's try to summarize this deep dive. We have gone from the Big Bang, where hydrogen was born.
Yeah, to the inside of Jupiter where it turns into a metal. We've looked at the spin isomers that make storing it a huge headache.
We've discussed how we strip it from fossil fuels, how we split water to make it green.
And the tantalizing possibility of mining it directly from the Earth.
We've seen how it feeds the world through ammonia and powers rockets into orbit, and we've looked at the invisible flames and the cracking pipes.
It really is the element of everything. It is the beginning, and in many ways, it is the future.
So what's the final thought for the listener? What should they be thinking about when they turn this off?
I want to go back to that geological surprise. For centuries, we have viewed hydrogen as an industrial product, something we have to manufacture. But the discovery of natural gold hydrogen reserves challenges that fundamental assumption. Are we standing on top of a resource that could decarbonize the planet without the massive energy cost of electrolysis? Or will it remain elusive, slipping through the cracks in the earth, just like it slips through our fingers?
That is the trillion-dollar question. Is the gold hydrogen rush real?
And a final personal thought. The next time you drink a glass of water, just remember, you are drinking star fuel that is burned. You are drinking the ash of the cosmos.
I will never look at a glass of water the same way again. Thanks for listening to The Deep Dive. Stay curious.
Bye, babe.